14.6 is a general approach to factoring. So in this section, we'll be reviewing all the different factoring techniques that we've learned in the previous couple of sections. General steps for factoring a polynomial is first to factor out any common factor. Then, if the polynomial is a binomial, meaning it has two terms, check to see if it's a difference of squares, the difference of cubes, or the sum of cubes. If it's a trinomial, meaning it has three terms, check to see if it's a perfect square trinomial. If it's not, factor the way we did in section 15.2 using FOIL or using grouping. If the polynomial has more than three terms, try to factor by grouping. And then step 3 is to always check by multiplying. If your expression is a binomial, then there are three possibilities. It can either be a difference of squares, which is x squared minus y squared, and the pattern was x plus y times x minus y. It can be a difference of cubes, or it can be a sum of cubes. If it's not one of those three types of binomials, then it cannot be factored. If your expression is a trinomial, meaning it has three terms, you need to decide whether it's a perfect square trinomial, which is x squared plus 2x plus y squared, or x squared minus 2xy plus y squared. In that case, it would be a perfect square, which is x plus y squared, or x minus y squared, depending on the sign. If it is not a perfect square trinomial, then we use the general factoring methods of factoring by grouping or FOIL, or simply just taking out a GCF. So step 1 is to factor out any common factors. So on A, 8x minus 80, they have a common factor of 8. So if I factor out the 8, I'm left with x minus 10. And then I have a binomial x minus 10, and I need to check if that's a difference of squares, no. Difference of cubes, no. Sum of cubes, no. So this is as much as I could factor. All I could do for this one was take out a GCF. On B, 2x cubed minus plus 10x squared minus 2x. So I can factor out a GCF of 2x first, leaving me with x squared plus 5x minus 1. Now I have a trinomial, x squared plus 5x minus 1, and x squared, I have a minus 1, so it can't be a perfect square, so I'm going to factor that by finding something that multiplies to negative 1 and adds to 5, and there's nothing that's going to give me that. So this is my factored form. For C, notice that I have two terms. So this is one term, and this is another term. They both have a common p minus q, so I'm going to pull out a p minus q, and then when I divide both sides by p minus q, I'm left with 12m minus 7n. Example 2 is factor each polynomial. So a is 36x squared minus y squared. That is a difference of two squares. So it's going to factor into 6x plus y times 6x minus y. B is 4t squared plus 1. They're both perfect squares, but it's a sum, and there's not a shortcut that I can use. There's not a way to factor a sum of two squares, so this one's prime. And there's not a GCF for me to pull out or anything. C is 125x cubed minus 27y cubed. So that's a binomial, and it's a difference of two perfect cubes. So the cube root of 125, x cubed is 5x, and 27y cubed is 3y. So this is going to be 5x minus 3y times a squared, so 25x squared plus, remember the sign changes, a times b, so 15xy plus b squared, so 9y squared. Okay, when you are working with a sum and a difference of sum and a difference of cubes, and your second factor is a trinomial, you can't factor that any further. That trinomial is always going to work out that it's as factored as you can get it. So, like in this case, you might look at it and say, well, 25x squared and 9y squared are perfect squares. But if I went and tried the perfect square trinomial trick, so this would be 5x and 3x, and I would have to, 3y, and I would multiply them and then double it. So there would be 15, doubled would be 30. Well, the middle term is not 30, it's just the 15. So that's one thing, you don't have to worry about it when you're doing the sum and difference of cubes. You can't factor it any further. Alright, so d x cubed plus 343y cubed, so the cube root is x and 7y. So it's going to be x plus 7y times x squared, and then the sign changes to the opposite, minus a times b, so 7xy plus b squared, 49y squared. Again, remember, you have to memorize this pattern, and you should always go back and check it to make sure that you remember the pattern correctly and it multiplies out to what it should be. Alright, so for factoring trinomials, we need to check first to see if it's a perfect square trinomial, and if it's not, then we just use one of the general ways of factoring. So on a, 16m squared plus 56m plus 49. Now my first and last terms are perfect squares, so that's 4m and 7. So if I multiply those together and double it, that's 28. Doubled is 56. So this would be 4m plus 7 squared. On b, r squared is a perfect square, but 72 is not. There's not a GCF, so I'm going to factor this one. By making my table, I need something that multiplies to 72 and adds to 18. So 8 times 9 is 17. 36 times 2 is 38. 6 times 12 is 18. So this is going to be r plus 6 times r plus 12. 8t squared minus 13t plus 5. So those are not perfect squares. There's no GCF. So I will factor this by grouping. So I need two numbers that multiply to positive 40 and add to negative 13. And I found that that was negative 5 times negative 8. So I'm going to rewrite this as 8t squared minus 5t minus 8t plus 5. Break that up into two groups. So it's going to be t times 8t minus 5. And then on this next one, there's nothing in common. There's a negative in the front, so I'm going to pull out a negative 1, which is going to give me 8t minus 5. So they have a common 8t minus 5, and my other factor would be t minus 1. On D, 6x squared minus 3x minus 63, we have a common factor of 3. So that'll leave me with 2x squared minus x minus 21. And then I can factor that further. 2x times x, and then 3 times 7, so it would give me 7 and 6, and I want a negative 1. So I have 3 times 2x minus 7 times x plus 3. And of course, factoring by grouping would have worked also. On problems like example 4, where there are more than 3 terms, you have to factor by grouping. So if I cut this in half, I can pull out a 5, and that leaves me with 4 minus m, and I can pull out a negative 3 to leave me with a negative 3n. And that leaves me with 4 minus m. So they both have a 4 minus m in common. And my second factor would be 5 minus 3n. B also has 4 factors, 4 terms. So I'll factor it by grouping again. So I can pull out p, leaving me with p squared minus 2q squared. And I can pull out a q, leaving me with p squared minus 2q squared. So they both have a p squared minus 2q squared, and then p plus q. And this is not cannot be factored further because of the 2, because 2 is not a perfect square. But if it was p squared minus q squared, or p squared minus 4q squared, you would have had to go one more step further. Okay, and 16 minus y squared is a difference of squares. So I can write that as 4 plus y, 4 minus y. Okay, now the problem with this is that they have nothing in common. So I'm going to scratch that. And regroup it. So notice that also 9x squared is a perfect square, so I'm going to regroup that with the y squared. So I'm going to rewrite it as 24x plus 16 plus 9x squared minus y squared, and try this grouping instead. So I can pull out an 8, leaving me with x plus 3x plus 2. And then on my perfect squares would factor to 3x plus y times 3x minus y, which still has nothing in common. So this cannot be factored, making it a prime polynomial.